Functions have been around for a very long time, probably 800 years or so. And the definition of what it is has been changing from person to person. Probably the late 1800s is when there was a formal definition of it that we use today. It's a specific and very special relation between two sets of numbers. Before we can talk about functions, we have to understand what a relation is. And here I've got two relations. A relation can be any kind of designated relationship between numbers. You can just state them as I have here. They can be a relation designated by some kind of equation or some other kind of complex mathematical structure, whatever that might be. In this case, like I said, I've just stated that these numbers are related. I have my first relation here and another one right here. To talk about relations, we typically use balloon bubbles that are like a way of designating what's called the domain and range. So I'm going to do that here. What I'm going to do is I'm going to look at these coordinate pairs. That's all I have here is a set of coordinate pairs that's in a specific relation, the first relation that I have. And in the first balloon, I'm going to put all of the x values, which are all of the first values there. Is 6, 3, 7, and -5. Okay. And in the second balloon, I'm going to put all my y values. That's the second value in all of the coordinate pairs. And -5 is already there. Now, to show the relation, I'm going to draw an arrow going from the first balloon to the second balloon as designated by each of these. So 6 go to the -7, like that. 3 to -5, 7 to 7, and -5 to -5. So what I've drawn here is the relation that's designated in the just set notation that I have on the top there. This is just the set notation for it. This is the graphical representation. It's kind of like algebraic versus geometric. It's just a different interpretation. And the balloon with all of the x variables, or the x values, is called the domain. This is also called the independent values or variables. And the second bubble is called the range, also called the codomain. Sometimes we call the second bubble the image, and therefore the first would be the pre-image. These are all the same kinds of things, talking about the same ideas. I'm going to talk about the domain and range, though, for this video. Okay, the next one, let's talk about the next one here. We have the x values, which is actually just 4. And the y values is 7, 8, and 9. And doing the same type of thing, 4 goes to 7, 4 goes to 8, and 4 goes to 9. So we once again have the domain, which is just 4, and the range, which is 7, 8, and 9. Now these are very different relations here. The first one, we call it a function. The second one, we do not call it a function. In fact, the only word we really have for it is just a relation, the general term for all these things. It is not a function, I should say. Not a function. And what tells you if it's a function or not, all you have to do is look at the domain values and look to see that there's only one thing coming out of it. 3 has only one thing, 7 has only one thing, and 5 has only one thing. On the other one, we have 3 lines coming out of the 4. And that's what tells you if it's a function or not. If there's only one line coming out of each one of the domain values, then you're good to go. If there's more than one, then you're not. it does not matter how many lines are coming into the range values, right? There's 2 here, but that's fine. Each one of these is only 1, but it doesn't matter. The red side is the only one that matters. There are other things in mathematics that matter for the green side, specifically one thing called one-to-one, and also onto is another thing, but that's not in the scope of this video. An important question is, why do we have this one specific idea that's so important to defining a function versus not a function? And that really depends on saying, if I input something, what's my output? And the output needs to be a single number. That way you can input a unique thing and you get out some number. You don't get out 2 numbers. It's always a unique answer. And whereas this one here, right, I input 4 and I get 3 numbers out, and I have to choose now between the 3, and it can be chaotic and not really sure which one we want. A function is more very specified. Like, you plug something in, you get something out. That's typically what a machine or what a function is kind of notified as a machine. You plug in some input and you get out some output. And the function is just the machine that changes its input to the output. Typically, it's some algebraic equation, and that's what we're going to be working with here. Another way of finding out a function, if it's a function or not, is using what's called the vertical line test. For this test, you have to have the graph, which we have here. So is x squared plus y to the 5th power equal to 6. Is this a function? Well, this is the graph of that. And what we do is we do the vertical line test. In other words, take a vertical line and cross it. And keep taking as many as you want, wherever they are, wherever you want to put them. And as long as every single vertical line crosses only once, then you have a function. Now, of course, for most of this graph, it's pretty straightforward. The only real question is right here. And I can't zoom in on this graph, but I could tell you that if you did zoom in, if you zoomed in very, very close to right here, you'll see eventually it looks something like this. And you can take vertical lines wherever you want along there, and it will in fact only cross once. And it's because it only crosses once every single time, yes, it is a function. That's the vertical line test. Okay, let's look at some of the algebraic forms of a function. Function notation always has this f of x. X is the input that you're plugging into your function, and f of x designates the what the function is equal to. In this case, f of x, the function is going to be 4x plus 6. This right here, the 4x plus 6, is what's in the black box. So x is what we get put into the box. Inside here, we have 4x plus 6. That's the function. And the output, which is going to be f of x, this depends on whatever x you plug in. We will only ever get one output, no matter what x we plug in. Like we're not going to get 2 outputs from this. So in this first case, we're plugging in -3. So f of -3, all you have to do is plug -3, the input, into the corresponding x value. Let me clean this up, show you. -3 is x. That means it goes to wherever x corresponds in the function. There can be as many x's as you want in the function. Every single one of them gets changed to -3. In this case, we have 4 times -3 plus 6. 4 times -3 is -12. And -12 plus 6 is -6. So if we input -3, then our function gives us an output of -6. We've changed -3 into -6. Let's continue. Instead of plugging in just an input or just a number, we can actually plug in other algebraic structures. In this case, we have x plus 7. So let's plug in x plus 7 the same way we did with -3. 4 times x, which is x plus 7 now, plus 6. Now we're going to simplify this thing by distributing. 4 times 7 is 28. And we get 34. So if you plug in x plus 7 into our function, we get out 4x plus 34. Since we plugged in not just a number, we plugged in a, actually it's technically another function. If you plug that in, you're going to get out not a number, but another function. Sometimes it'll cancel and you'll get just a number, but in this case it did not. Okay, here we're plugging in negative x. 4 times negative x plus 6. 4 times negative x is just negative 4x. And that's what we get there. All right, let's try a little bit more complex of a function. Plugging in 3 gives us 3 times y, which is 3 squared, minus 1 over y squared, which is 3 squared, right? The y's get plugged into both of the y spots, just like this y goes there and that y goes there. Now all we have to do is simplify. So order of operations says 3 squared is first, 3 squared is 9. Multiplication, 3 squared is 9. 3 times 9 is 27. 27 minus 1 is 26 over 9. And that cannot reduce, so I'm going to leave it like that. Plugging in negative 3. 3 times y squared, so negative 3 squared, minus 1, over y squared, so negative 3 squared. Negative 3 squared is 9. Negative 3 squared is 9. 3 times 9 is 27, minus 1. And we get 26 over 9. The same answer, right? So that makes us wonder, well, if we plug in something and the negative of itself, what happens? This should be y here. Let me change that. What happens if instead of taking just g of y, like we have here, we use instead g of negative y? Since 3 and negative 3 worked, it would be the same thing. What do we get here? So plugging in g of negative y gives us 3 times negative y squared minus 1 over negative y squared. Negative y squared is negative y times negative y, right? Negative y squared equals negative y times negative y, which equals y squared. 3y squared minus 1 over y squared. But this is our function. This is just g of y. So we found that g of negative y equals g of y, which doesn't mean much right now. It's going to mean more in the coming sections. But that's just an interesting property of this function. Okay, here we have an elaborate setting. We have f of negative x minus f of x when we have defined f of x equals x cubed minus 3x plus 2. The first thing I'm going to do is figure out what is f of negative x, because I know what f of x is. That's just this, which is this. F of negative x I don't know, but I can find that by plugging in negative x into f of x. Hope that makes sense. Let me clean it up and get going. So f of x we already know is x cubed minus x plus 2. F of negative x then is going to be negative x cubed minus negative x plus 2. Negative x cubed, negative x times negative x times negative x, 2 cancels, and we get negative x cubed. So we have minus x cubed. Those two negatives cancel, we get plus x plus 2. So that's what f of negative x equals. Now we take f of negative x, what we just found. Let me write it this way. F of negative x minus f of x. F of negative x is this. F of x is that. Minus, I'm going to put this in parentheses because that minus is going to distribute into everything. So just doing some of the algebra. Negative x cubed plus x minus 2. You see we have like terms here. The 2's cancel. So we get negative 2x cubed plus 2x. All right, here I have another function, and this one is actually called a trigonometric function. We could solve this algebraically if you knew how to handle trig functions with the algebra of it. We haven't gone over that in this class, but we can still solve this geometrically. If we have the graph, which we do right here, right? This is just this graph right here. Then f of 4, this first problem, is saying what happens when you plug 4 into our function. In other words, if 4 is the x coordinate, what's the y coordinate? And that's going to be y equal to 4. So f of 4 equals 4. Now, f of negative 1 says what happens when we plug negative 1 into the function. We go up or down in the function, but we don't go anywhere. The function crosses right there. And so actually, that's the point we look at, which is going to be y equal to 0. Right, f of negative 2, we go over to negative 2. What happens when we plug this value into our function? We go up or down to our function. In this case, we have to go down. That's where the function is designated at. Go over to the y-axis, and that's at negative 4. So f of negative 2 is negative 4. We always go up or down to wherever the function is. If we don't have to go up or down, like we did here for the blue, that means that it's going to be equal to 0. All right, here I have a graph. We're going to ask certain questions about this. What's the domain? What's the range? What are the x and y intercepts? And what's the value of f of 3? First off, the domain is all of the x values that the function is kind of like over or below, if that makes sense. In other words, you should be able to draw down to the x, draw down or up to the x-axis, all of the values that the line is over. And we look at the corresponding interval on the x-axis. Now, if there's an open dot like there is on the ends here, that means that value is not included in it, but it does include every value up to or down to that interval. In other words, we use a parenthesis at an open dot. At a closed dot, we use a bracket, square bracket. So this blue interval here from 0 up to 5, that is the domain. From 0 up to 5. And you see that it kind of covers the function. I'll draw the function in purple here. Right, we go from this point here all the way through up to this point here. And that interval covers all of the x values, right? All of them go like that. Hopefully that makes sense. Clean this up. Okay. Now the range is the same thing, but for the y values. So for the green, we're just going to go all the way back to the green. In this case, we go to is equals to 6 there. And likewise, we just continue, all of these values here, all the way on down to there. So we're going to go from negative 4 on up to 6. Again, we do not include the endpoints because they're open dots. That's why we use parentheses there instead of square brackets. That's how you find the range. You just collapse it to the y-axis and look at what's the range values there. Okay, the x-intercept is where does the graph cross the x-axis. It actually crosses right here. I kind of removed the drawing since with all the blue and green. And that's at 2. So there's a couple ways you could say this. You could say this at 2, 0. That's the point, right? That's that point there, 2, 0. You could also say x equal to 2 because an x-intercept has to have y equal to 0. So another way you could say this is just saying 2 because you know y must equal 0. Likewise, the y-intercept is when x equals 0 and it crosses the y-axis. Of course, down here, you see that's an open dot. That's the only spot that it would cross the y-axis, but it doesn't. So we do not have any y-intercepts. None. If this were a closed dot, this would be a y-intercept, but it's not. Okay, f of 3. If you can see the graph here, let me see if I can clean up just a tiny bit. F of 3, it says take 3, go up to the graph, and go over to the y-axis. That's going to be this number right here, which is 2. So f of 3 is 2. My graph, I know all the values it should be. The graphs that you deal with are going to be much nicer, and it should be very easy to see kind of where like f of 3 would be. All right, let's look at another one. Okay, the domain. We're looking for all of the values that go to the x-axis, sorry. And like continuing, you see all of these things are down there. And in fact, it goes on indefinitely this way, and it goes on indefinitely that way. And what that means is that all of the x values are included in this domain. So we include everything. What's the interval that includes everything? That's from negative infinity to positive infinity. All of the real numbers are included in this function's domain. Range, we just collapse it to the y-axis. And you see a lot of them are included. And the question is, what happens for this thing? Does it keep going on down towards this x-axis here? And in fact, it does. This is called an asymptote. It's going to be a horizontal asymptote. That means it gets infinitely close to it, but it never crosses or even touches the x-axis. So we go from 0, but do not include it. That's the asymptote part. On up to infinity, because you can definitely see that this continues on indefinitely upwards. So all of these y values on up are included in our range. Okay, the x-intercept is where does this function cross the x-axis. I just told you, however, that this is an asymptote, and so this never crosses the x-axis. So there is no x-intercept. The y-intercept is where does it cross the y-axis, and it crosses it right there, which is at 1. You could say 0, 1. That's the coordinate pair of that point. You could also say y equal to 1, because that means that's where the y value is. And you could also just say 1, because x is always going to be assumed to be 0. That's what it means for a y-intercept to be something, is that x equals 0. F of 2, we go up to 2, and we go over, and this hits 4. Okay. Let's look at this one here. Here we're just wondering what the domain range is. So going down, we see we start right here at this point, and all of this stuff is included all the way on up to here, but this point is not included because it's an open dot. So we go from 0 on up to 5. So our domain, the 0 point is closed dot, meaning that it is included when we have a closed dot here, that's what this, I drew a 0. Oh, whoops. I drew a dot there. It should just be a black dot like that. That's a closed dot, meaning that it's included in the function of the graph. This, of course, is an open dot, so it's not included. That's why the 0 has a bracket and the 5 has a parenthesis. Likewise, the range, we just go on up. All of this is included, and this point right here, which is the top point, is included, and that goes to 6 here. So the bottom point's included, the top is included. We have 0 to 6. And even though this you know, kind of curls back, that's fine. It's just that's all still in the range.